Hello and welcome. My name is Saili Gokhale. In accordance with the subject of Manufacturing Processes 2 of third year Mechanical Engineering for SPPU syllabus, I am conducting this session. It will cover the Unit 4 named Advanced Machining Processes in three parts A, B, and C. Let us start with Part A. Learning outcomes or the final results of this part are getting acquainted with the different types of advanced machining process, that is their classification according to energy forms used for machining, and to understand the need of advanced machining process, which will be explained by the shortcomings of currently used or conventional machining processes, which we covered in the last units. This part will also include the study of electrical discharge machining with coherence to the point principles, working, process parameters, advantages, limitations, and application of EDM. Contents of this presentation include classification, need, and EDM. Let us see the details of classifications of advanced machining processes. They are classified on the basis of energy forms used. The mechanical advanced machining processes includes ultrasonic machining, which uses sound energy, abrasive jet machining, water jet machining, and abrasive flow machining. Electrochemical processes, which uses electricity and chemical processes for the machining, are electrochemical machining, which includes electrochemical grinding, milling, and drilling. Then the electrothermal, which uses electricity and thermal energy in combination for machining. This includes electrical discharge machining, laser beam machining, and electron beam machining. Then the purely chemical processes, which are chemical milling and photochemical milling. Chemical processes are used as finishing processes in most of the cases. Out of this, ultrasonic machining, abrasive jet machining, electrochemical machining, electric discharge machining, and laser beam machining we are going to see in details in this unit. So, what is the need of these machining processes? In traditional machining processes like turning, milling, grinding, there is a direct contact between tool and workpiece. Also, large forces are required to remove the materials in the forms of chip and abrasion, and high generation is accompanied to this machining. This induces residual stresses and decreases the life and quality of the workpieces. Also, conventional machining processes, the tool is essentially harder than the workpiece. Hence, some restrictions are there in conventional machining. The first one is the workpiece with high strength and hardness, that is more than 400 HP, cannot be machined. We know that the technology is vastly improving day by day, and high tech industries like aerospace, transport, and energy sectors have demands of engineering materials with superior properties like high strength, hardness, super finish, high temperature resistance, and many more. This cannot be achieved by conventional machining. Another aspect is demands of plastic, ceramics, and composites are increasing, but these are both harder and brittle for the conventional machining. So they cannot be machined using conventional machining processes. The another aspects are slender and flexible or hard to clamp jobs cannot be machined using conventional machining processes. Complex parts, long or small holes are also difficult to machine. The special surface and dimensional tolerance requirement, that is super finish, is also difficult to be achieved by conventional machining process. So let us now see the details of advanced machining processes. Firstly, let's understand the details of electrical discharge machining. The principal use for electrical discharge machining is material removed by spark erosion due to spark generation between workpiece and tool. This spark generates high temperature and pressure between tool and workpiece, which removes material by erosion and evaporation. Let's see. Let's see the construction and working of electrical discharge machining. This process is also called as spark erosion process. This is a standard setup used for electrical discharge machining. We have tool, which is usually made up of copper, graphite, or copper tungsten alloys and connected to the negative terminal of the supply to be used as cathode. Then the workpiece, which is usually connected to the positive terminal of the supply to be used as anode. The gap between the tool and the workpiece is called as inter-electrode gap or simply the spark gap. The tool and the electrode tip is submerged in a dielectric fluid bath, which is constantly recirculated through pump and filtered for impurities by filter. The tool is equipped with servo control for vertical motion of the tool and in turn controlling the spark gap. The DC pulse generator is a power source of whole equipment and it is used for generating high voltage pulse between the spark gap. Let us examine the inter-electrode spark gap for a single spark erosion. Actual electrical discharge machining is happening in the spark gap. The electrode spark gap is nothing but the gap between the tool, which is negative or cathodic, and the workpiece, which is positive or anodic. As pulse from DC generator reaches the gap, an intense electrical field develops in a gap. This causes microscopic contaminants and particles to retract and concentrate in gap, which creates a high conductivity bridge inside the gap. As field voltage increases, the bridge heats up and some particles get ionized to form a spark channel between electrodes, which gives rise to visible spark. This creates high pressure and heat at the spark contact point, and the metal from the workpiece and even electrode is vaporized to form a vapor bubble, which expands to cut off the spark. This bubble is then cooled as the spark ends from the generator and the electrical fluid rushes in and flushes out the solidified metal particles from the workpiece and the gap. The whole process leaves the machined workpiece at the spark contact. The process parameter normally includes voltage up to 300 volts, current up to 400 amperes, spark gap of 0.0125 to 0.125 mm. Then pulse duration can be 2 to 2000 microseconds depending upon the surface of workpiece and the tool used. The material removal rate is usually ranges between 800 millimeter cube to 5000 millimeter cube. Advantages of electrical discharge machining includes the material hardness can be ignored. Any type of material can be machined using this. The hardness doesn't matter. Then the smooth machining surface and polishing are not required as the tolerance achieved is 0.005 mm. No stress concentration at tool and workpiece as there is a no direct contact between tool and workpiece in this process. The wear of the electrode is negligible and complex shapes can be easily produced using EDM. Production rate is high and machine can be easily operated for a longer time. Just filtering and pumping of the electrolyte is needed. This process has some disadvantages. One of them is only conductive materials can be machined using this, as the workpiece is supposed to be anodic and it should conduct electricity for spark generation. Then, this process is more expensive than the conventional machining process as it requires a DC pulse generator and a separate pump and filter arrangement, also dielectric fluid bath. Applications of EDM are in various sectors like aerospace, automobile, and energy. It is used for drilling very small holes and making parts at irregular shape with precision for forging press tool, extrusion dies, cutting tool dies. It is used for making pattern on tool steel dies. It is also used for cutting intricate and complicated controls. It is used in the sectors like aerospace, electronics, medical, and semiconductor industries, and used for cutting the electrically conductive metals such as aluminium, brass, copper, carbide, steel, and titanium. So, this is it for part A. Let's hope to see you in part B.